Tonight, we're going to answer a question that sounds simple, but will change everything. What is the true scale of the universe? Not the numbers you've heard before, not the facts you think you understand. The actual, visceral reality of how distance and size work in space. And more importantly, how small is Earth within all of this? Because when you zoom out from Earth, through the solar system, through the galaxy, through superclusters and cosmic filaments, something happens. The scales become so extreme that words like big and far stop meaning anything. And by the end of tonight, you're going to understand why light takes hours just to cross our solar system, why Earth becomes completely invisible from distances we can still observe, and why the observable universe itself, stretching 93 billion light-years across, might be infinitely small compared to what lies beyond. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Right now, you're somewhere on Earth's surface. Maybe you're in a room. Maybe you're outside. Wherever you are, look around. What you see feels real, substantial, permanent. Buildings, streets, trees, mountains in the distance, if you're lucky. This is the scale where human life happens. Everything that matters to you personally exists at this scale. Your home, your city, the places you've traveled. From your perspective, Earth is enormous. You could spend years traveling and still not see every corner of it. Earth's circumference at the equator is about 25,000 miles. If you could walk continuously at 3 miles per hour, 8 hours every day, it would take you about 3 years to walk around the world. Most people never travel more than a few thousand miles from where they were born. Earth, from a human perspective, is vast. More than enough world for a lifetime of exploration. But let's start changing our perspective. Imagine you're in an airplane at cruising altitude, about 6 miles up. From here, entire cities fit in your field of view. You can see the curve of the horizon starting to become apparent. The ground below looks like a map. Individual cars and houses are invisible. Only large features are visible. The boundaries between city and countryside. Already, at just 6 miles up, Earth starts to feel bigger than your everyday experience suggested. You can see so much more. But you're still clearly on a planet, looking down at its surface. Now, jump much higher, to the International Space Station, orbiting at about 250 miles up. From here, the view changes dramatically. You can see the curvature of Earth clearly. The horizon bends away in an obvious arc. The atmosphere appears as a thin blue line along the edge of the planet. It's shockingly thin. The entire atmosphere, all the air we breathe, all the weather, all the clouds, compressed into a layer so thin it looks painted on. Astronauts describe this view as profound. Earth looks beautiful but fragile, and you can see how small it is. From the space station, you're seeing roughly 3% of Earth's surface at any given moment. Weather patterns are visible as swirling masses of white clouds. Hurricanes look like giant spirals. You can watch thunderstorms from above, seeing lightning flash inside the clouds. At night, cities glow like clusters of lights. The Terminator, the line between day and night, sweeps across the surface as Earth rotates. You can see sunrise happening in real time, the shadow of night rolling westward. This is already a perspective very few humans have experienced. Only about 600 people have ever been to space. For the rest of us, Earth remains the ground beneath our feet, not a sphere floating in void. But 250 miles is nothing. Let's go farther, much farther, to the Moon, 240,000 miles from Earth. This is the farthest distance humans have ever traveled. 12 people walked on the Moon's surface between 1969 and 1972. The journey took 3 days. From the Moon, looking back at Earth, our planet appears small. It's still the brightest object in the sky, still clearly identifiable, but it's no longer overwhelming. It fits easily in your field of view. You can cover it with your thumb. The astronauts describe seeing Earth rise over the Moon's horizon, a fragile blue marble in the black void. This image, Earthrise, became one of the most famous photographs ever taken. It changed how humanity saw itself. For the first time, we could see our entire world as a single object, remote and vulnerable. The Moon itself is about 2,200 miles in diameter, about 1/4 the size of Earth. If you were standing on the Moon, looking up at Earth, Earth would appear about 4 times larger than the Moon appears from Earth. Still impressive, but clearly distant. The Moon's surface is grey and lifeless, covered in craters from billions of years of asteroid impacts. No atmosphere, no water, no life. Just rock and dust. During the Apollo missions, astronauts left footprints in the lunar dust. Those footprints are still there today. With no wind or weather to erase them, they'll remain for millions of years. A permanent mark of humanity's brief visit to another world. Now let's make a much bigger jump to one astronomical unit, 93 million miles. This is the average distance from Earth to the Sunday. From here, Earth is barely visible. You need to know exactly where to look or you'll miss it entirely. It's a pale blue dot, a pixel of light. The Moon is completely invisible. Too small and too dim to see. If you didn't have precise coordinates, you'd never find Earth in the blackness. But the Sun dominates everything. It's a brilliant sphere, far too bright to look at directly, even from this distance. The Sun's diameter is about 865,000 miles. That's 109 times wider than Earth. If the Sun were hollow, you could fit about 1.3 million Earths inside it. The Sun contains 99.86% of all the mass in the solar system. Everything else, all 8 planets, all their moons, all the asteroids, comets, and dust, all of it combined, makes up less than 1/5 of 1%. The Sun is not just the center of the solar system. It is the solar system. Everything else is debris. The Sun is a star, a massive ball of hydrogen and helium undergoing nuclear fusion. In its core, hydrogen atoms slam together with enough force and heat to fuse into helium, releasing tremendous energy. This process has been happening for 4.6 billion years and will continue for another 5 billion. The energy radiates outward from the core, taking thousands of years to work its way to the surface. Once it reaches the surface, it streams off into space as light and heat. Earth intercepts a tiny fraction of this energy. Most of it radiates away into empty space, traveling outward forever unless it hits something. Our solar system has 8 planets arranged in order by distance from the Sun: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. The inner 4 are rocky worlds with solid surfaces. The outer 4 are gas and ice giants, with no solid surface to stand on. Let's talk about the distances between these planets, because this is where scale starts becoming difficult to grasp. Mercury orbits at 36 million miles from the Sunday. Venus at 67 million. Earth at 93 million. Mars at 142 million. These are the inner planets, relatively close to the Sunday. Close enough that light from the sun reaches them in just minutes. But then, there's a big gap. Jupiter orbits at 484 million miles, more than 5 times farther than Earth. Saturn is at 890 million miles. Uranus at 1.8 billion miles. Neptune at 2.8 billion miles. Neptune is 30 times farther from the Sun than Earth is. Light from the Sun takes 4 hours to reach Neptune. If something happened on the Sun right now, we'd see it in 8 minutes. Neptune wouldn't see it for 4 hours. The distances are staggering. If you could drive a car at highway speed, about 70 miles per hour, continuously without stopping, it would take you 150 years just to drive from Earth to the Sunday. You'd die of old age before completing the trip. Driving to Neptune at the same speed would take more than 4,500 years. That's longer than recorded human civilization. You'd need hundreds of generations to complete the journey. This is the scale of just our local neighborhood. Just the space between planets orbiting a single, ordinary star. And we haven't even left the solar system yet. Beyond Neptune lies the Kuiper Belt, a donut-shaped region filled with icy bodies left over from the solar system's formation. Pluto orbits here, along with thousands of other frozen objects. The Kuiper Belt extends from about 30 astronomical units to 50 astronomical units. 1 astronomical unit is the Earth-Sun distance, 93 million miles. So, the Kuiper Belt stretches from about 2.8 billion miles to about 4.6 billion miles from the Sunday. Light takes 4 to 7 hours to cross this region. Beyond the Kuiper Belt is an even more remote region, the Oort cloud, a theoretical, spherical shell of icy objects surrounding the entire solar system. The Oort cloud extends from about 2,000 astronomical units out to possibly 100,000 astronomical units. That's nearly 2 light-years at its outer edge. A light-year is the distance light travels in 1 year. Light moves at 671 million miles per hour. In 1 year, it covers about 5.88 trillion miles. The Oort cloud's outer edge is about 1.9 light-years away. Light from the Sun takes almost 2 years to reach it. Objects in the Oort cloud orbit the Sun so slowly that a single orbit takes millions of years. We've never actually seen the Oort cloud. It's too far and too sparse. But we know it's there because of long-period comets. These comets take hundreds or thousands of years to orbit the Sunday. Their orbits are so elongated that they spend most of their time in the distant Oort cloud, only rarely swooping in close to the Sunday. When they do, the Sun's heat vaporizes their ice, creating the glowing tails we associate with comets. So the solar system, from the Sun out to the Oort cloud's edge, spans about 2 light-years. That's the full extent of the Sun's gravitational dominance. And here's the key point. Most of this space is empty. The planets occupy a tiny fraction near the center. The Sun sits at the middle. The 8 planets all orbit within about 3 billion miles. That sounds huge, but it's nothing compared to the Oort cloud, stretching out to nearly 12 trillion miles. If you made a scale model where the Sun was the size of a basketball, Earth would be a tiny ball about 83 feet away. Neptune would be half a mile away. And the Oort cloud would extend out about 30 miles in all directions. That's the solar system. A basketball, a few microscopic planets nearby, and a spherical boundary 30 miles away. Everything else is empty space. Now comes the truly mind-bending part. The nearest star to our Sun is Proxima Centauri. It's 4.24 light-years away, about 25 trillion miles. In our basketball model, Proxima Centauri would be another basketball 16,000 miles away. That's more than halfway around Earth. The nearest star to us is so distant that if we shrink the Sun to basketball size, the nearest neighbor is on the other side of the planet. This is the structure of space. Tiny islands of matter separated by incomprehensible voids. If you could travel at the speed of the Voyager 1 spacecraft, the fastest object humans have ever built, moving at about 38,000 miles per hour, it would take 73,000 years to reach Proxima Centauri. 73,000 years. Longer than human civilization has existed. We launched Voyager in 1977. If it were headed toward Proxima Centauri, which it's not, it wouldn't arrive until the year 75,000. The distances between stars are so vast that interstellar travel remains science fiction. We can barely leave our own solar system, let alone reach another star. But stars aren't scattered randomly through space. They cluster together into galaxies. Our Sun is part of the Milky Way galaxy. The Milky Way is a barred spiral galaxy containing between 100 billion and 400 billion stars. That's a conservative estimate. It might have more. Each star, potentially, has planets. Many probably do. Current estimates suggest there are more planets than stars in our galaxy. Hundreds of billions of worlds orbiting hundreds of billions of suns. The Milky Way has a diameter of about 100,000 light-years. Light takes 100,000 years to cross from one side to the other. Our Sun is located about 26,000 light-years from the galactic center, in a minor spiral arm called the Orion Spur. We're between two major arms, in a relatively quiet region. The Sun orbits the galactic center at about 490,000 miles per hour. At this speed, one complete orbit takes about 225 million years. We call this a galactic year. The last time the Sun was in its current position, dinosaurs were just beginning to evolve on Earth. The time before that, life on Earth was still mostly confined to the oceans. The Sun has completed only about 20 orbits since it formed 4.6 billion years ago. 20 trips around the galaxy in its entire life. From our perspective, the galaxy seems eternal and unchanging. But it's rotating, evolving, changing slowly over timescales we can barely comprehend. The Milky Way doesn't exist in isolation. It's part of a group of galaxies called the Local Group. The Local Group contains more than 50 galaxies. Most are small dwarf galaxies with only a few billion stars each. But there are two giants, the Milky Way and Andromeda. Andromeda is slightly larger than the Milky Way, containing about 1 trillion stars. It's a spiral galaxy like ours, and it's about 2.5 million light-years away. The light you see from Andromeda tonight left that galaxy 2.5 million years ago, when early humans were just learning to use stone tools. You're not seeing Andromeda as it exists right now. You're seeing its past. The current Andromeda is invisible to you, and will remain so for another 2.5 million years until the light it's emitting now finally reaches Earth. The local group spans about 10 million light-years. All the galaxies in it are gravitationally bound together. They orbit a common center of mass. And the Milky Way and Andromeda are actually moving toward each other. In about 4 billion years, they'll collide. The collision will be slow and majestic. Individual stars probably won't hit each other because stars are so small and space is so empty. But the galaxies will interpenetrate, their shapes distorting, their spiral arms pulled apart by tidal forces. Gas clouds will collide, triggering bursts of star formation. The supermassive black holes at each galaxy's center will eventually merge. The process will take hundreds of millions of years. When it's finished, a new elliptical galaxy will exist where the Milky Way and Andromeda once were. But the local group is just one small structure in a much larger hierarchy. The local group is part of the Virgo supercluster. A supercluster is a massive collection of galaxy groups and galaxy clusters spread across hundreds of millions of light-years. The Virgo supercluster contains at least 100 galaxy groups and clusters, more than 47,000 galaxies total. The largest structure within it is the Virgo cluster, about 53 million light-years away, containing 1,000 to 2,000 galaxies packed into a relatively small volume. The Virgo supercluster has a diameter of about 110 million light-years. Within this volume, galaxies aren't evenly distributed. They cluster along filaments, creating dense regions where thousands of galaxies congregate. Between the filaments are voids, vast, empty regions where very few galaxies exist. This pattern, filaments and voids, appears at all large scales in the universe. It's called the cosmic web. But even the Virgo supercluster is part of something larger. In 2014, astronomers discovered that our supercluster is actually part of an even bigger structure called Laniakea. The name means immeasurable heaven in Hawaiian. Laniakea contains about 100,000 galaxies spread across 520 million light-years. It's not a gravitationally bound structure like a galaxy or cluster. Instead, it's defined by the flow of galaxies within it. All the galaxies in Laniakea are moving in coordinated ways, pulled by the gravitational influence of dense regions. One of those dense regions is called the Great Attractor. We can't see it directly because it's hidden behind the plane of the Milky Way. Dust and stars in our own galaxy block our view, but we can measure its gravitational effect. It's pulling hundreds of thousands of galaxies toward it, including ours, at speeds of several hundred miles per second. Our galaxy, along with everything else in our corner of Laniakea, is flowing toward the Great Attractor. We won't get there for billions of years. And by then, the expansion of the universe might have carried it beyond our reach. But for now, we're being pulled. Laniakea is just one of many similar superclusters scattered throughout space. There are structures even larger. The Sloan Great Wall is a cosmic filament about 1.37 billion light-years long. The Hercules, Corona, Borealis, Great Wall is even bigger, about 10 billion light-years across. That's 73% of the diameter of the observable universe. Structures this large challenge our understanding of how the universe works. According to the cosmological principle, the universe should look roughly the same in all directions on large enough scales. But a structure 10 billion light-years across suggests there's significant variation even at the largest scales we can observe. These walls and filaments are part of the cosmic web, If you could zoom out and see billions of light years in every direction, you'd see a web-like pattern. Dense filaments of galaxies stretching across space, connecting massive nodes where thousands of galaxies cluster together. Threading through everything are the voids. Enormous bubbles of empty space, hundreds of millions of light years across. These voids aren't completely empty. They contain some scattered galaxies, but they're much less dense than the filaments. The cosmic web formed from gravity, acting on tiny density fluctuations in the early universe. Regions that were slightly denser than average pulled in more matter, becoming even denser. Regions that were less dense expanded faster, becoming emptier. Over billions of years, this process created the structure we see today. Now, we reach the boundary of what we can observe, the observable universe. This is not the edge of the universe itself. The universe might be infinite. We don't know. But the observable universe is the region from which light has had time to reach us since the Big Bang. The Big Bang occurred 13.77 billion years ago. But because space has been expanding while light traveled toward us, the observable universe is larger than you'd expect. About 46.5 billion light-years in radius, 93 billion light-years in diameter. Everything within this sphere is potentially observable. We can receive light from it. Everything beyond is outside our observable universe. Light from those regions hasn't reached us yet, and because the universe's expansion is accelerating, there are regions whose light will never reach us. The space between us and them is expanding faster than light can travel through it. These regions are beyond the cosmic event horizon, permanently inaccessible. The observable universe contains an estimated 2 trillion galaxies. 2 million galaxies, each containing anywhere from a few million to several trillion stars. If we assume an average of 100 billion stars per galaxy, that's 200 billion trillion stars total. That's 2 with 23 zeros after it. 200 sextillion stars. And most of those stars probably have planets. Current estimates suggest multiple planets per star on average, which means there could be hundreds of sextillions of planets in the observable universe. Some fraction of those planets are in their star's habitable zone, the region where temperatures allow liquid water. Some fraction of those actually have liquid water. Some fraction might have life. We don't know these fractions. We only have Earth as an example. But even if life is extraordinarily rare, the numbers are so large that there could be millions or billions of living worlds. Let's put Earth's size in perspective against all of this. Earth's diameter is about 7,900 miles. The observable universe's diameter is 93 billion light-years. That's about 880 trillion miles. The ratio is about 700 sextillion to 1. The observable universe is 700 sextillion times wider than Earth. If Earth were 1 millimeter across, the size of a pinhead, the observable universe would be 700 billion miles across. That's about 100 times the distance from the Sun to Pluto. But comparing diameters doesn't capture the full disparity. Volume scales with the cube of diameter. The observable universe's volume, compared to Earth's volume, is roughly 3.4 times 10 to the 72nd power. That's a 3.4 followed by 72 zeros. There's no way to visualize this number. It's too large for human comprehension. You could fit that many Earths inside the observable universe's volume. But the number is so enormous, it's meaningless to us. This is the challenge of understanding cosmic scale. Our brains evolved to handle everyday problems. How far to walk, to find water. How high that tree is, how deep that ravine. We're good at distances measured in steps or hours. We're terrible at cosmic scales. When you hear billion or trillion or sextillion, they're just words. You can't feel the difference between them. And when you get to numbers like 10 to the 72, all intuition fails. We can calculate it. We can write it down. But we cannot understand it viscerally. But let's try a different approach. Instead of thinking about size, think about what cosmic scale reveals about the universe's nature. First, the universe is old, 13.77 billion years, nearly 3 times older than Earth. In that time, countless generations of stars have lived and died. The first stars formed just a few 100 million years after the Big Bang. They were massive, short-lived, composed only of hydrogen and helium. When they died in supernova explosions, they scattered heavier elements into space: carbon, oxygen, iron, silicon. These elements mixed with primordial hydrogen and helium. The next generation of stars that formed had more complex chemistry. This cycle repeated over billions of years, each generation of stars enriching space with heavier elements. Earth is made from the ashes of multiple generations of dead stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all created in stellar cores billions of years ago. You are literally made of stardust. Second, the universe is structured, not random. Matter clusters on every scale. Particles form atoms. Atoms form molecules. Molecules form dust. Dust forms planets. Planets orbit stars. Stars cluster into galaxies. Galaxies cluster into groups. Groups into clusters. Clusters into superclusters. Superclusters into filaments, outlining voids. This hierarchy exists because of gravity. Gravity pulls matter together. Wherever matter is slightly denser than average, gravity pulls in more matter, amplifying the difference. Dense regions get denser. Sparse regions get sparser. Over billions of years, this creates structure. The cosmic web is the result of gravity acting on tiny, random fluctuations in the early universe. Third, the universe is expanding. In the 1920s, Edwin Hubble discovered that distant galaxies are moving away from us. The farther they are, the faster they're receding. This pattern is exactly what you'd expect if space itself is expanding. It's not that galaxies are moving through space. Space is expanding, and galaxies are carried along with it. If you run time backward, the expansion leads to a point where everything was compressed into an infinitely small, infinitely dense state. The Big Bang. Not an explosion in space, but an explosion of space itself. The beginning of space and time. Fourth, the universe is mostly empty. We've emphasized this throughout, but it bears repeating. The distances between objects are vastly larger than the objects themselves. Most of the universe's volume contains nothing, no matter, no light, just expanding space. And even where matter exists, most is dark matter. About 27% of the universe's total mass energy. Dark matter doesn't interact with light. We can't see it directly. We only know it exists because of its gravitational effects on visible matter. Galaxies rotate faster than they should based on visible mass alone. Clusters contain more mass than we can account for. Gravitational lensing reveals unseen mass-bending light, all pointing to dark matter's existence. But we don't know what it's made of. Then there's dark energy. about 68% of the universe's mass energy. Dark energy is even more mysterious than dark matter. It's a property of space itself. Every cubic meter of space has a small amount of dark energy. As space expands, creating more volume, more dark energy comes into existence. The effect is that dark energy drives accelerating expansion. The universe isn't just expanding. It's expanding faster and faster. This was discovered in 1998 and came as a complete surprise. Most physicists expected expansion to be slowing due to gravity. Instead, it's speeding up. Only about 5% of the universe is ordinary matter, the stuff we're made of, atoms, protons and neutrons and electrons, stars and planets and gas and dust. Everything we can see, everything we've ever touched, everything we know directly is less than 5% of what exists. The rest is dark matter and dark energy. Phenomena we observe but don't understand. This should be humbling. We've figured out an enormous amount about the universe, but most of it remains mysterious. Now, let's consider what this scale means for life. Earth is one planet among hundreds of sextillions. If even a tiny fraction of planets have conditions suitable for life, there could be countless living worlds. We haven't found evidence of extraterrestrial life yet. But absence of evidence isn't evidence of absence. The universe is vast, and we've barely begun searching. In recent decades, we've discovered thousands of exoplanets. Some are Earth-sized. Some orbit in habitable zones. Some might have atmospheres and liquid water. We're developing telescopes that can analyze exoplanet atmospheres, looking for biosignatures, gases that might indicate life. Oxygen and methane, in the right combinations, could be strong evidence. This search is ongoing. In coming decades, we might discover life elsewhere, or we might find that life is extremely rare. Either way would be profound. If life is common, the universe is filled with living worlds. Billions or trillions of planets with ecosystems and evolution, maybe even intelligence. This would raise the Fermi paradox. If intelligent life is common, where is everybody? We see no signs of other civilizations, no signals, no megastructures, nothing. The universe appears silent. There are many possible explanations. Maybe civilizations destroy themselves before becoming spacefaring. Maybe intelligence is rare. Maybe civilizations exist, but are too far apart in space and time to ever meet. The universe is so large and so old that two civilizations could arise and die without ever knowing each other existed. Or maybe we're first. Maybe Earth is the first planet to develop technological intelligence. Somebody has to be first. The universe is only 13.77 billion years old. Stars will keep burning for trillions of years. Most of cosmic history is still ahead. Maybe intelligent life arose early on Earth, and countless other civilizations will follow billions of years from now. If life is rare, that makes Earth precious, not in a geocentric way. Earth isn't the center of anything, but it would mean our planet has something most don't. That would make life and consciousness incredibly valuable. We'd be alone, or nearly alone, in a vast cosmos. The responsibility for spreading life would fall to us. No one else is coming. If we want the universe filled with life and consciousness, we have to do it. We have to survive our current challenges and develop the technology to travel between stars. Let's consider humanity's place in all this. We're on Earth. Earth orbits the Sunday. The Sun is one of 200 billion stars in the Milky Way. The Milky Way is one of 50 galaxies in the local group. The local group is part of the Virgo supercluster. The Virgo supercluster is part of Laniakea. Laniakea is one structure among millions in the observable universe. At each level, we become smaller, less significant, more isolated. From Earth's surface, we feel important. We're the center of our experience. But zoom out, and we're one person among 8 billion. Zoom out further, and Earth is one planet among trillions of trillions. Our galaxy is one among 2 trillion. Our supercluster, one among millions. This perspective can feel crushing. We're infinitesimally small. Our lives are brief. Our concerns local. The universe doesn't care about us. It operates according to physical laws without regard for human hopes or fears. Stars burn, galaxies collide, space expands, entropy increases, all following mathematical rules that have no concept of purpose or meaning. If we disappeared tomorrow, the universe would continue unchanged. Stars would keep shining. Galaxies would keep moving. Nothing would be different, except on Earth. And in a few million years, geological processes would erase all trace we existed. But here's the counterpoint. Yes, we're small. Yes, the universe is vast and indifferent. But we're here. We exist. And we can understand all this. That's remarkable. We're matter that became aware of itself. We're the universe experiencing itself. Every thought, every question about existence is the cosmos reflecting on its own nature. You're not separate from the universe. You're part of it, made from it. When you think about stars, you're using atoms from stars. When you contemplate the Big Bang, you're using energy that originated there. Moreover, consciousness might be rare and precious. We don't know if it's common or if it requires special conditions that rarely occur. If consciousness is rare, if most of the universe is non-conscious matter following physical laws, then every conscious being is valuable. Every moment of awareness is a small miracle. You're experiencing something most of the universe cannot. That makes your existence significant, even if the universe is indifferent. And we're not passive observers. Our actions matter on human scales. We can't control galaxy rotation or cosmic expansion. But we can control what happens on Earth. We can choose how we treat each other. We can preserve or destroy our environment. We can develop beneficial or destructive technologies. We can work toward a future where humanity thrives or one where we destroy ourselves. These choices matter, not to the universe, but to us, and that's enough. The scale of the universe teaches many lessons. It teaches humility. We're not the center. We're not special, cosmically. We're a tiny part of an enormous whole. It teaches perspective. Our problems, while real, are local and temporary. It teaches interconnection. We're made of the same stuff as stars. We follow the same physical laws as galaxies. We're part of the cosmic web, linked through gravity and space and time to everything that exists. And most importantly, it teaches us about the power of human curiosity and reason. Despite being tiny creatures on a small planet, we've figured out the universe's structure. We've measured it, mapped it, understood it. We've traced its history from the Big Bang to today and predicted its future billions of years hence. This achievement required millennia of observation, centuries of experimentation, decades of theory. It required telescopes that see across billions of light years, computers that simulate cosmic evolution, mathematical frameworks describing curved spacetime. We built all this. We invented the tools, developed the theories, made the observations, assembled the pieces. No one gave us this knowledge. We earned it through work, creativity, persistence. And we're not done. There's more to discover. Dark matter and dark energy remain mysterious. We don't fully understand the Big Bang or what came before. We haven't found life elsewhere yet. We don't know if the universe is finite or infinite. These mysteries are exciting, not frustrating. They mean science isn't finished. Let's explore some of the most extreme phenomena in the universe to really appreciate the scales we're dealing with. Consider quasars. These are among the brightest objects in existence. A quasar is powered by a supermassive black hole at the center of a distant galaxy. As matter spirals into the black hole, it heats to millions of degrees and emits tremendous radiation. A single quasar can outshine its entire host galaxy. That means one black hole, probably only a few light-hours across, emits more light than hundreds of billions of stars combined. The brightest quasars are visible from billions of light-years away. When we observe a quasar 10 billion light-years distant, we're seeing it as it was 10 billion years ago, when the universe was less than 4 billion years old. Quasars were much more common in the early universe. This tells us something about cosmic evolution. Young galaxies were smaller, gas-rich, and collisions were frequent. These conditions fed supermassive black holes, creating quasars. As the universe aged, galaxies spread apart, collisions became rare, gas supplies dwindled, and quasar activity declined. Most supermassive black holes today are dormant, not actively consuming large amounts of matter. Now, think about gamma-ray bursts. These are the most energetic explosions since the Big Bang. A gamma-ray burst releases more energy in seconds than the Sun will emit in its entire 10 billion-year lifetime. The cause is thought to be either a massive star collapsing into a black hole or two neutron stars merging. In both cases, jets of material are launched at nearly light speed. When these jets point toward Earth, we detect a brief, intense flash of gamma rays, lasting milliseconds to minutes. Gamma ray bursts are so bright, we can detect them from across the observable universe. The most distant one detected came from when the universe was only 630 million years old. That light traveled for over 13 billion years to reach us. The energy output is staggering, about 10 to the 46 joules in a few seconds. The Sun's total output over its entire life will be about 10 to the 44th joules. A gamma-ray burst releases 100 times more energy than the Sun's entire lifetime output in just seconds. If one occurred within a few thousand light-years of Earth with its jet pointed at us, it would be catastrophic. The intense radiation would strip our ozone layer, exposing the surface to deadly ultraviolet. It could trigger mass extinction. Fortunately, gamma-ray bursts are rare, and the odds of one harming us are very small. But it reminds us the universe contains phenomena of incredible violence and power. Consider pulsars. A pulsar is a rapidly rotating neutron star emitting beams of radiation from its magnetic poles. As it rotates, the beams sweep across space like a lighthouse. If Earth lies in a beam's path, we detect regular pulses. hence the name. Pulsars are incredibly dense. A neutron star packs about 1.4 solar masses into a sphere only about 12 miles across. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The density is so extreme that atomic nuclei touch each other with no empty space between atoms like in normal matter. The fastest known pulsar rotates 716 times per second. 716 complete rotations every second. Its surface moves at about 20% light speed. It's hard to imagine an object spinning that fast, especially with the mass of the Sunday. The Sun, trying to rotate that fast, would tear itself apart. Centrifugal force would overcome gravity. But for a neutron star, gravity is strong enough to hold everything together, even at these extreme rotation speeds. Black holes take density even further. A black hole is a region where gravity is so strong, nothing, not even light, can escape. The boundary is the event horizon. Once anything crosses it, it's trapped forever. All paths through space-time led inward toward the singularity at the center. Black holes come in different sizes. Stellar mass black holes from collapsed stars have masses between 3 and a few dozen solar masses. Supermassive black holes at galaxy centers have masses from millions to billions of solar masses. The Milky Way's central black hole, Sagittarius A star, has about 4.3 million solar masses. Despite this enormous mass, its event horizon is only about 7.3 million miles in radius, smaller than Mercury's orbit. The supermassive black hole at M87 center has about 6.5 billion solar masses. Its event horizon has a radius of about 11.8 billion miles, larger than Pluto's orbit. This black hole is so massive, the Event Horizon Telescope imaged its shadow in 2019. The image shows a dark region surrounded by a bright ring of hot gas spiraling inward. Black holes challenge physics. At the singularity, density becomes infinite and known physics breaks down. We need quantum gravity to understand what happens there. But we don't have that theory yet. General relativity and quantum mechanics, our two most successful theories, are incompatible at black hole singularity scales. This is one of the biggest open problems in theoretical physics. Another mystery is the information paradox. Quantum mechanics says information is never lost. But if something falls into a black hole, it seems to disappear. The black hole eventually evaporates through Hawking radiation. It's unclear if information comes back out or is lost forever. Stephen Hawking spent decades on this problem. He eventually proposed information is somehow preserved, but details are still debated. Let's think about cosmic timescales more explicitly. The universe is 13.77 billion years old. But what does that mean practically? The Big Bang occurred 13.77 billion years ago. In the first fraction of a second, inflation expanded the universe exponentially. By 1 second old, it had cooled enough for protons and neutrons to form. By 3 minutes old, nuclear fusion created helium and small amounts of lithium. The universe was still too hot for atoms. It was a plasma of nuclei and electrons, opaque to light. At about 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. This is recombination. When it happened, light could suddenly travel freely without being absorbed by free electrons. This light is what we see as the cosmic microwave background, the oldest light in the universe. a snapshot from when it was 380,000 years old. That light has traveled through expanding space for 13.39 billion years. Expansion stretched it, redshifting it from visible to microwave radiation. But it's still there, coming from every direction, a relic of early history. For hundreds of millions of years after recombination, the universe was dark. No stars yet, no galaxies. Just hydrogen and helium gas cooling and clumping under gravity. This period is the cosmic dark ages. It ended when the first stars formed, probably around 100 to 200 million years after the Big Bang. These first stars were massive, hundreds of times more massive than the Sunday. They burned hot and fast, living only millions of years before exploding as supernovae. Their explosions enriched space with the first heavy elements: carbon, oxygen, silicon, iron. These mixed with primordial hydrogen and helium. The next generation of stars had slightly more complex chemistry. Galaxies formed from mergers of smaller structures. Early galaxies were small and irregular, containing millions rather than billions of stars. They collided and merged, building up the large spirals and ellipticals we see today. The Milky Way formed this way. It started small and grew by consuming smaller galaxies. This continues today. The Milky Way is currently consuming several dwarf galaxies. Streams of stars pulled from them flow through our galaxy's halo. Astronomers have mapped several streams, tracing disrupted dwarfs being torn apart by the Milky Way's gravity. Our solar system, formed about 4.6 billion years ago, 9.2 billion years after the Big Bang. The universe was already old. Many star generations had lived and died. The gas cloud that collapsed to form the solar system contained elements from earlier stars. This is why Earth has heavy elements. They weren't created in the Big Bang. They were created in stellar cores and supernovae, dispersed into space, then incorporated into the solar system. Earth formed shortly after the Sun, within about 50 to 100 million years. Early Earth was hellish, bombarded by asteroids and comets. So hot, its surface was mostly molten. No oxygen in the atmosphere, no oceans, certainly no life. But conditions improved. Bombardment slowed. The surface cooled and solidified. Water vapor condensed, forming the first oceans. By about 4 billion years ago, Earth had liquid oceans and possibly a thin atmosphere. Sometime around 3.7 to 4 billion years ago, life appeared. We don't know exactly when or how. The fossil record from this era is sparse. But by 3.5 billion years ago, there's clear evidence of microbial life. Simple, single cells, probably living in oceans or hydrothermal vents. For most of Earth's history, life remained simple, single cells, bacteria and archaea, nothing you could see without a microscope. This lasted about 3 billion years. Think about that. 3 billion years of Earth's 4.54 billion year history, roughly 66% of the time life existed, was single-cellular. Complex multicellular life didn't appear until about 800 million years ago. Animals with hard shells and skeletons didn't appear until about 540 million years ago during the Cambrian explosion. Life on land is even more recent. Plants colonized land about 470 million years ago. Animals followed shortly after. Dinosaurs appeared about 230 million years ago and went extinct 66 million years ago. Humans, genus Homo, appeared about 2 to 3 million years ago. Modern humans, Homo sapiens, appeared about 300,000 years ago. Recorded history goes back only about 5,000 years. Everything we consider ancient civilization happened in the last tiny fraction of Earth's history. If you compressed Earth's entire history into 24 hours, life would appear around 4 a.m. Complex life would appear around 8:30 p.m. Dinosaurs would exist from about 11 p.m. until 11:41 p.m. Humans would appear in the last few seconds before midnight. Recorded history would be the last tenth of a second. Your life would be an immeasurably brief flash. This temporal scale is as humbling as spatial scale. We exist for a blink. Earth has existed for a third of the universe's age. The universe itself, as old as it is young compared to how long it will exist. Stars will keep forming and burning for trillions of years. Low-mass red dwarfs can burn for 10 trillion years or more. The universe is currently 13.77 billion years old. The smallest red dwarfs forming today will still shine 10 trillion years from now, long after the sun dies, long after most galaxies merge, long after star formation ends. The universe will look completely different then. Most stars will have exhausted fuel. Galaxies will be filled with white dwarfs, neutron stars, black holes. The night sky will be dark, with only a few dim red stars remaining. Eventually, even those fade. Black holes will be the last large structures, sitting in an expanding void, slowly evaporating via Hawking radiation over timescales of 10 to the 100th power years. That's the deep future. An incomprehensibly distant time when the universe is cold, dark, nearly empty. All structure erased by entropy. All energy dissipated. This is heat death, the ultimate fate predicted by thermodynamics. But we don't need to worry. It's so far in the future, the numbers become meaningless. For now, the universe is vibrant, full of stars and galaxies and interesting phenomena. One challenge in comprehending cosmic scale is using analogies and models. But even the best analogies break down. If you represent the observable universe as Earth, each galaxy would be about bacterial cell size. You couldn't see individual galaxies without a microscope. If you represented a galaxy as Earth, each star would be microscopic, smaller than pollen. If you represented the Milky Way as the United States, the solar system would be smaller than a pinhead. These comparisons help, but they're imperfect. They give relative size, sense, but not true understanding. Maybe better is thinking about what you could see from different locations. Standing on Earth, looking up, you see thousands of stars on a dark night. Every one is in the Milky Way, most within a few thousand light years. The farthest naked eye star is probably V762 Cassiopeae, about 16,000 light years away. That's the human vision limit, without instruments. Everything beyond is too faint or hidden by dust. Now imagine you're on a planet in Andromeda, looking toward the Milky Way. The Milky Way would appear as a faint smudge, similar to how Andromeda looks from Earth. With a telescope, you could resolve individual bright stars in the Milky Way's spiral arms, but most would be a blur. From Andromeda, the Milky Way would be beautiful, but distant, unreachable with current technology. Now imagine you're in a Virgo cluster galaxy, 53 million light-years from the Milky Way. The Milky Way would be invisible to naked eyes. You'd need a telescope to see it at all, and even then, it's a tiny smudge, one of countless similar smudges across the sky. From the Virgo cluster, The Milky Way is just another galaxy. Not special, not remarkable, just another star island. Now, imagine you're at the observable universe's edge, 46.5 billion light-years away. Looking toward where the Milky Way is now, you'd see nothing. Light from the Milky Way hasn't reached that distance yet. Or if it has, expansion redshifted it beyond detection. From the observable edge, the Milky Way doesn't exist yet in your past light cone. You're seeing a younger universe, before our galaxy formed. This is what makes cosmology strange. Distance and time are linked. Looking far away means looking back in time. When we observe a galaxy 10 billion light-years away, we see it as it was 10 billion years ago, when the universe was only 3.77 billion years old. That galaxy might not exist anymore. It might have merged with another, or been torn apart by tidal forces, or simply evolved beyond recognition. We have no way of knowing what it looks like now. Now is not accessible. We can only see the past. The farther we look, the deeper into the past we see. This creates a cosmic horizon. Beyond a certain distance, we're looking back before stars and galaxies formed. We see only the cosmic microwave background from 380,000 years after the Big Bang. Nothing before that is directly visible because the universe was opaque. There's also a future horizon. Because expansion accelerates, there's a distance beyond which light will never reach us, no matter how long we wait. Galaxies beyond this are receding faster than light can travel, through expanding space between us and them. This doesn't violate relativity. Nothing moves through space faster than light. But space itself, expanding, has no speed limit. These distant galaxies will fade over billions of years, their light stretched to longer wavelengths, redshifted beyond detection. Eventually, only galaxies gravitationally bound to our local group remain visible. Everything else will have receded beyond the cosmic horizon. If intelligent beings exist trillions of years from now, they'll see a much emptier universe. Most galaxies gone, carried away by expansion. They'll have to reconstruct universe history from local evidence, much harder than what we can do today. Let's think about the cosmic microwave background more carefully. This radiation is the Big Bang's afterglow. It comes from every direction, almost perfectly uniform. The temperature is about 2.7 Kelvin everywhere, about 2.7 degrees above absolute zero. Very cold. But the temperature isn't exactly uniform. There are tiny fluctuations, about 1 part in 100,000, some regions slightly hotter, some slightly cooler. These fluctuations represent tiny density variations in the early universe. Regions slightly denser than average. These overdense regions had slightly more gravity, attracting more matter, becoming denser. Over hundreds of millions of years, tiny fluctuations grew into galaxies and clusters. The cosmic microwave background is essentially a baby picture showing seeds that later grew into all cosmic structure. By studying fluctuation patterns, cosmologists determine key universe properties: total matter and energy, the ratio of ordinary matter to dark energy, universe age, expansion rate, space geometry, all from analyzing the microwave background. It's one of cosmology's most important observations. NASA's Wilkinson Microwave Anisotropy Probe and ESA's Planck satellite mapped it with incredible precision. The result is a detailed picture of the universe at 380,000 years old, embedded with information about composition, history, and fate. Another key observation is distant galaxy redshift. When Edwin Hubble observed galaxies in the 1920s, he noticed something peculiar. Light from distant galaxies shifted toward redder wavelengths. The farther the galaxy, the greater the redshift. This pattern was universal. Almost every galaxy showed redshift. Only a handful of nearby galaxies showed blue shift, indicating they're moving toward us. Hubble interpreted this as evidence the universe expands. If space expands, light traveling through it gets stretched, increasing wavelength, shifting toward red. Redshift amount tells you how much space expanded while light was in transit. Larger redshifts mean greater expansion, greater distance, longer travel time. Astronomers use redshift as a distance indicator. They measure a galaxy's redshift, estimate distance, then observe properties. By observing thousands of galaxies at different redshifts, they trace cosmic expansion history, measure how the rate changed over time, and determine what's causing acceleration. The discovery that expansion accelerates, announced in 1998, was a shock. Most physicists expected expansion to slow. Gravity should pull everything together, decelerating expansion. But observations showed the opposite. Expansion speeds up. Something pushes space apart, counteracting gravity. That something is dark energy. Dark energy makes up about 68% of the universe's total mass energy. It's a space property. Every cubic meter has a small amount. As space expands, creating more cubic meters, more dark energy comes into existence. This seems to violate energy conservation, but doesn't due to general relativity's strange bookkeeping. The effect is dark energy's density remains constant, while expansion continues, while matter density decreases. In the early universe, matter dominated. So much matter packed into small volume that its gravity controlled expansion. But as the universe expanded, matter spread out, becoming less dense. Dark energy density didn't change. Eventually, about 5 billion years ago, dark energy became dominant. Since then, it's driven accelerating expansion. Dark energy's nature is unknown. The simplest explanation is the cosmological constant, a term Einstein added to general relativity equations. Einstein introduced it to allow a static universe. The prevailing belief, then, when Hubble discovered expansion, Einstein supposedly called the cosmological constant his greatest blunder and removed it. But it turns out the cosmological constant might be real, just not for Einstein's reason. If dark energy is the cosmological constant, its vacuum energy property, empty space itself. The quantum vacuum isn't actually empty. Virtual particles constantly pop in and out of existence. These quantum fluctuations have energy. If you add energy from all fluctuations, you get a number that could act like the cosmological constant. But here's the problem. When you do the calculation, the predicted cosmological constant value is about 10 to the 120th power times larger than observed, off by 120 orders of magnitude. The worst prediction in physics history. Something is clearly wrong with our understanding. Maybe dark energy isn't the cosmological constant. Maybe it's something dynamic, a field changing over time. This is called quintessence. Or maybe general relativity is wrong on large scales. Gravity doesn't work the way we think when applied to the entire universe. These are active research areas. Astronomers try to measure dark energy properties more precisely. Is its density truly constant over time, or does it change? Is it uniform throughout space, or does it vary from place to place? These questions will help narrow what dark energy could be. Future telescopes and surveys will provide better data, but for now, dark energy remains mysterious. We know it exists because we measure its effects, but we don't know what it is. Dark matter is similarly mysterious. We know it exists because we see gravitational effects, but we've never detected it directly. Dark matter doesn't emit, absorb, or reflect light. It doesn't interact electromagnetically at all, as far as we can tell. It only interacts through gravity and possibly the weak nuclear force, though that's uncertain. Multiple evidence lines point to dark matter existence. Galaxy rotation curves show galaxies rotate faster than they should based on visible mass alone. Gravitational lensing shows clusters contain more mass than visible matter accounts for. The cosmic microwave background's fluctuation pattern matches predictions only if dark matter exists. Structure formation simulations show the cosmic web can't form without dark matter. All observations are consistent with invisible matter interacting only gravitationally. But what's it made of? The leading candidate is WIMPs, weakly interacting massive particles. Hypothetical particles with mass somewhere between 10 and 10,000 proton masses. They don't interact electromagnetically, so they're invisible. They interact only weakly, rarely colliding with ordinary matter. WIMPs are predicted by certain standard model extensions, theories going beyond current understanding. Several experiments tried to detect WIMPs directly. They use large detectors placed deep underground to shield from cosmic rays. The idea is WIMPs, from the dark matter halo surrounding our galaxy, occasionally pass through. Once in a rare while, a WIMP collides with an atomic nucleus in the detector, depositing tiny energy. By detecting these collisions, scientists hope to discover dark matter particles directly. So far, no conclusive detection. Other dark matter candidates exist. Axions are another possibility. Extremely light particles predicted by certain theories. Or dark matter could be primordial black holes formed in the early universe, floating around since. Or something entirely different we haven't thought of. The search continues. Understanding dark matter is one of physics and astronomy's biggest goals. It's a fundamental universe component, most of the matter that exists. Figuring out what it is would be a major breakthrough. But even without knowing what dark matter is, we can study its distribution and effects. We can map it using gravitational lensing. We can simulate how it clusters and forms structure. We can understand its role in galaxy formation and evolution. Dark matter is essential for understanding large-scale structure. Without it, galaxies wouldn't form. Stars wouldn't form. We wouldn't exist. In a universe without dark matter, tiny early density fluctuations couldn't grow. Normal matter has pressure. When it clumps, pressure pushes back, resisting further collapse. Dark matter doesn't have pressure. It can clump freely. This makes it the scaffolding on which galaxies form. Normal matter falls into gravitational wells created by dark matter, accumulating in densest regions, eventually forming stars and galaxies. The cosmic web, that pattern of filaments and voids, is primarily a dark matter structure. Dark matter forms the web. Normal matter follows, lighting it up with stars and galaxies, revealing the underlying structure. Now, let's explore what happens when we try to comprehend these scales using numbers. Earth's diameter is about 7,900 miles. The observable universe's diameter is 93 billion light-years. Converting that to miles, it's about 546 sextillion miles. That's a 5.46 with 23 zeros after it. The ratio between the observable universe and Earth is about 700 sextillion to 1. If Earth were reduced to the size of a single atom, about 1/10 billionth of a meter across, the observable universe at that same scale would still be about 72 million miles across, larger than the actual distance from Earth to the Sunday. That's how extreme the scale difference is. Or think about it this way. The number of atoms in your body is about 7 times 10 to the 27th power. That's 7, followed by 27 zeros, a genuinely enormous number. But the number of atoms in your body is smaller than the ratio between the observable universe's volume and a sugar cube's volume. The universe is more voluminous compared to a sugar cube than a sugar cube is compared to an atom. These comparisons barely scratch the surface of conveying true scale. Because we're not just talking about size. We're talking about volume, which scales with the cube of diameter. The observable universe's volume, compared to Earth's volume, is about 3.4 times 10 to the 72nd power. That's incomprehensibly large. Let's try to build up to this number gradually. A million is 1,000 thousands. A billion is 1,000 millions. A trillion is 1,000 billions. A quadrillion is 1,000 trillions. A quintillion is 1,000 quadrillions. A sextillion is 1,000 quintillions. 10 to the 72 is 10,000 sextillion, sextillion, sextillion. There's no human experience that connects to numbers this large. They're just abstract symbols on a page. But they represent something real. The actual ratio between the volume of space we can observe and the volume of our planet. When you stand on Earth's surface and look up, you're seeing a minuscule fraction of what exists. The visible horizon is only a few miles away. From an airplane, you can see maybe 200 miles to the horizon. From the space station, you can see about 1,000 miles. From the moon, you can see half of Earth. But Earth itself is invisible once you're more than a few million miles away. It becomes a pale dot, requiring telescopes to see. And from across the universe, from distances measured in billions of light years, Earth doesn't just become invisible. It becomes literally undetectable. No telescope we could ever build could see Earth from that distance. This raises an interesting question. If Earth is invisible from most of the universe, are there other Earths invisible to us? Almost certainly, yes. At cosmic distances, we can only see the brightest objects, galaxies, quasars, bright star clusters. Individual stars are invisible beyond a certain distance. Planets are invisible much sooner. The most distant exoplanet we've detected is about 28,000 light-years away. That's impressive, but it's still within our own galaxy. We've never directly detected a planet in another galaxy. They're too small and too dim. The light from their parent star overwhelms them. This means there could be trillions of Earth-like planets throughout the universe that we'll never see. They're too far away, too faint, hidden behind the glare of their stars. We might detect them indirectly. We might see their gravitational effects or detect gases in their atmospheres. But we'll never see them as we see Jupiter or Saturn through a telescope, never see their continents or clouds or oceans. They exist in a realm beyond direct observation. Known to exist through inference and statistics, but individually unknowable. This is both humbling and exciting. Humbling because it reminds us how limited our view is. We see only the brightest, largest, most obvious structures. Everything else hides in darkness. But exciting because it means the universe contains vastly more than we can directly observe. More worlds, more diversity, more possibilities than we've catalogued. Let's think about the journey of light more explicitly. Light from the sun takes 8 minutes to reach Earth. That means we see the sun as it was 8 minutes ago. If the sun suddenly vanished, we wouldn't know for 8 minutes. We'd keep seeing it, keep feeling its warmth for those 8 minutes while the last photons traveled toward us. Then suddenly, it would blink out. The sky would go dark. Within an hour, the temperature would start dropping. Within days, the oceans would begin to freeze. But for those first 8 minutes, everything would seem normal. That's what it means for light to have finite speed. Information can't travel instantaneously. There's always a delay between an event and our knowledge of it. For nearby stars, this delay is measured in years. Alpha Centauri is 4.37 light-years away. If it exploded tonight, we wouldn't see it until 4.37 years from now. In the meantime, we'd see it shining normally, completely unaware it's already dead. For distant galaxies, the delay is measured in millions or billions of years. The Andromeda galaxy is 2.5 million light-years away. The light we see from it tonight is 2.5 million years old. Andromeda might look completely different now. It might have undergone a starburst, triggered by colliding with a dwarf galaxy. It might have merged with another large galaxy. We won't know for 2.5 million years. When we observe quasars, billions of light-years away, we're seeing the universe as it was billions of years ago. Those quasars might not exist anymore. They might have consumed all their fuel and faded. The galaxies hosting them might have merged with neighbors, creating new structures we can't yet see. We're observing ancient history, unable to see the present state of distant objects. This creates a strange situation. The farther we look in space, the farther back in time we see. If we could somehow observe a galaxy 10 billion light-years away and a galaxy 1 billion light-years away simultaneously, we'd be seeing two different epochs of cosmic history. The 10 billion light-year galaxy shows us the universe when it was young. The 1 billion light-year galaxy shows us a more recent era. They're not happening at the same time. They happen billions of years apart. But we see them at the same time because their light took different amounts of time to reach us. This is fundamentally different from how we experience time in everyday life. Normally, when we see two things happening, they're happening now, in our present. But in cosmology, simultaneous observations show events from different eras. It's like watching a historical documentary and a news broadcast at the same time. One shows you the past, one shows you the recent past, but you're experiencing both in your present moment. This intertwining of space and time is one of the most profound insights from relativity. Space and time aren't separate. They're woven together into spacetime. Movement through space affects passage through time. Gravity, which we think of as a force, is actually curved spacetime. Massive objects bend spacetime around them. Planets orbit stars not because they're being pulled, but because they're following straight paths through curved spacetime. This is hard to visualize. Spacetime is four-dimensional. 3 space dimensions and 1 time dimension. We can't picture 4 dimensions directly. Our brains evolved to handle 3. But mathematically, Four-dimensional spacetime is well defined and precisely described by general relativity. Einstein's equations tell us how matter and energy curve spacetime and how curved spacetime affects matter and energy motion. These equations have been tested extensively and have never failed. They predict things we've confirmed: the bending of starlight by the sun's gravity, the precession of Mercury's orbit, gravitational time dilation, gravitational redshift, the existence of black holes, gravitational waves. Gravitational waves are ripples in spacetime itself. When massive objects accelerate, they create waves that propagate outward at light speed. These waves stretch and squeeze spacetime as they pass. They're incredibly weak. Even waves from massive sources like merging black holes stretch spacetime by less than 1 part in 10 to the 21st power. That's less than the width of a proton compared to the distance to the nearest star. Detecting something that's small required building the most sensitive instruments ever created. The Laser Interferometer Gravitational Wave Observatory, LIGO, consists of 2 facilities separated by 2,000 miles. Each has 2 4-kilometer-long arms arranged in an L shape. Lasers bounce back and forth along the arms. When a gravitational wave passes through, it slightly changes the arm lengths. One arm gets slightly longer while the other gets slightly shorter. Then vice versa as the wave oscillates. The change is incredibly tiny, less than 1/10,000th the diameter of a proton, but LIGO can measure it. On September 14th, 2015, both LIGO detectors registered a gravitational wave signal. The signal matched predictions for 2 black holes spiraling together and merging. The black holes were about 30 solar masses each. They merged about 1.3 billion light-years away. The merger released more energy in a fraction of a second than all the stars in the observable universe combined emit in that same time. But it released this energy as gravitational waves, not light. So it was invisible to optical telescopes. Only gravitational wave detectors could see it. Since that first detection, LIGO and its partner Virgo have detected dozens of black hole mergers and several neutron star mergers. These observations tell us about extreme physics, how matter behaves at nuclear densities, how space-time behaves near black holes, how heavy elements are created in neutron star mergers. Gold, platinum, uranium, all the heavy elements are forged when neutron stars collide and explode. The gold in jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, all came from neutron star mergers billions of years ago. These elements were blasted into space, mixed with gas clouds, and eventually incorporated into planets like Earth. Like everything else, we're made from cosmic catastrophes. Now, let's think about the universe's future. We've discussed its past and present. What about what comes next? In the near term, the next few billion years, not much will change. Stars will continue forming, burning, and dying. Galaxies will continue merging. The cosmic web will continue evolving. But on longer timescales, major changes occur. In about 4 billion years, the Milky Way and Andromeda will collide. The merger will take hundreds of millions of years. During this time, Earth's night sky will look spectacular. Andromeda will fill much of the sky. Tidal tails will stream across the heavens. Star formation will surge as gas clouds collide, but Earth itself might not survive. The Sun will be nearing the end of its main sequence, life. In about 5 billion years, the Sun will exhaust its hydrogen fuel. It will expand into a red giant, its outer layers reaching beyond Earth's current orbit. Earth will either be consumed or sterilized by heat. If humanity still exists, we'll need to have left Earth by then. We'll need to colonize other star systems or find other solutions. This sounds like science fiction, but 5 billion years is a genuinely long time. Life has existed on Earth for about 3.7 billion years. In 5 billion years, evolution could produce outcomes we can't imagine. Perhaps our descendants will be unrecognizable. Perhaps they'll have spread throughout the galaxy. Perhaps they'll have technologies we can't conceive of. Or perhaps we'll be long extinct, replaced by some other form of life or intelligence. We don't know, but the Sun's lifespan is finite. Earth's habitability is temporary. Eventually, all suns die. After about 1 trillion years, star formation will essentially cease. All the available hydrogen and helium will be locked up in stars, planets, or stellar remnants. Or it will have been ejected from galaxies. The universe will enter a new era dominated by dead stars, white dwarfs, neutron stars, and black holes. Galaxies will be dark, containing only these remnants and the occasional dim red dwarf still burning. After about 100 trillion years, even the longest-lived red dwarfs will burn out. The universe will be completely dark, except for rare events like white dwarfs colliding or matter falling into black holes. Galaxies will begin to evaporate. Stars in galactic halos will be gravitationally ejected into intergalactic space. Clusters will dissolve. The cosmic web will come apart. After about 10 to the 30 years, assuming protons decay, which some theories predict, ordinary matter will disintegrate. Planets, asteroids, dead stars, all will slowly evaporate as their protons decay into lighter particles. After about 10 to the 40 years, only black holes remain. Everything else has decayed or fallen into them. The universe is cold, dark, and nearly empty. Black holes sit in isolation, separated by expanding voids. And even black holes don't last forever. Stephen Hawking showed that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation is incredibly weak for stellar or supermassive black holes. The radiation temperature is far below the cosmic microwave background temperature. So currently, black holes absorb more radiation than they emit, and they grow. But as the universe expands and cools, the background temperature will eventually drop below the Hawking radiation temperature. Then, black holes will start evaporating. The time this takes depends on the black hole's mass. A stellar mass black hole takes about 10 to the 67th years to evaporate. A supermassive black hole takes about 10 to the 100th years. These timescales are unimaginably long. 10 to the 100th years is a Google years. The universe's current age is only 13.77 billion years, about 10 to the 10th years. A Google years is 10 to the 90th power times longer. By the time the last black holes evaporate, the universe will be unrecognizably different from today. After black hole evaporation, the universe enters its final state, the dark era. Only radiation and a few isolated particles remain, spread across unimaginable distances. The temperature approaches absolute zero. Entropy approaches maximum. This is heat death. The universe continues existing, continues expanding, but nothing happens. No structure, no change, just endless expansion and cooling. This is the fate predicted by current physics and cosmology. It's bleak. But it's also so far in the future that it's almost meaningless to us. For trillions of years, the universe will remain interesting and dynamic. Stars will shine. Galaxies will exist. The possibility of life and intelligence will persist. We exist during the stelliferous era, the age of stars. This is the universe, at its most vibrant and diverse. We're fortunate to exist now, rather than in the distant future or the distant past. Let's consider what all this means for human existence and meaning. We're tiny creatures on a tiny planet in a vast universe. Our lives are brief. The universe is ancient and will exist for incomprehensible time after we're gone. Individual humans typically live 70 to 80 years. Human civilization is about 10,000 years old. Our species is about 300,000 years old. The universe is 13.77 billion years old. The ratio between a human lifetime and the universe's age is about 1 to 200 million. You live for about 1/200 millionth of the time the universe has existed. That's brief beyond comprehension. And spatially, we're even more insignificant. A human body is about 6 feet tall. The observable universe is 93 billion light-years across. Converting to the same units, the observable universe is about 1.5 times 10 to the 27th feet across. The ratio is about 1 to 2.5 times 10 to the 26th. You're about 1/250 septillionth the size of the observable universe. These numbers are so extreme, they lose meaning. You can't visualize being 1/200 million times briefer than something. You can't picture being 1 septillionth the size of something. The numbers are just numbers, but they represent reality. You really are that small and brief compared to the cosmos. This could lead to nihilism. If we're so insignificant, why does anything matter? Why should we care about our lives, our loves, our achievements? The universe doesn't care. It will continue, whether we exist or not. In the grand cosmic scheme, we're nothing. But this misses something crucial. Significance doesn't require cosmic importance. It requires importance to someone. Your life matters to you. It matters to people who know and care about you. The fact that the universe is indifferent doesn't erase these very real connections and experiences. Pain is still pain. Joy is still joy. Love is still love. These don't become less real just because they occur on a tiny planet in a vast cosmos. Moreover, we might be rare. If consciousness is uncommon in the universe, then every conscious being is precious, regardless of size or duration. We don't know how common consciousness is. We've never found it anywhere but Earth. If it's rare, then every moment of awareness is special. You're experiencing something most of the universe cannot. Subjective experience. Qualia, the redness of red. The painfulness of pain. The love you feel for someone. These are real phenomena. They exist. They matter, at least to you. And that's enough. Mattering doesn't have to be universal to be genuine. There's also the perspective that we're not separate from the universe. We're part of it. Every atom in your body came from the Big Bang or from stars. The hydrogen in your body, about 10% of your atoms, is primordial. It's been around since the first few minutes after the Big Bang. It's 13.7 billion years old. The heavier elements in your body, carbon, nitrogen, oxygen, were created in stars billions of years ago, then dispersed by supernovae. You're not outside the universe looking in. You're the universe, arranged in a particular way, a way that's conscious, a way that can think and feel and wonder. In a very real sense, you're how the universe experiences itself. When you look at stars, the universe is looking at itself. When you think about the Big Bang, the universe is contemplating its own origin. This doesn't make you cosmically important, but it makes you cosmically connected. You're not an isolated thing. You're a pattern in the cosmic tapestry. And there's the achievement of understanding. Despite being tiny and brief, humans have figured out the universe's structure. We've measured its age, size, and composition. We've discovered how stars work, how galaxies form, how the cosmos evolves. This required millennia of observation and centuries of theory. It required thousands of people working across generations, each building on previous work. No single person could have done it. It's a cumulative achievement of civilization. And it continues. Every year, we learn more. Every decade brings new discoveries. We're nowhere near finished understanding the universe. There are still mysteries. Dark matter, dark energy, quantum gravity, the nature of consciousness, the possibility of life elsewhere. These questions will occupy scientists for generations. Let's explore the search for life beyond Earth in more detail, because it directly relates to understanding our scale and significance. For most of human history, we could only speculate about other worlds. We knew other planets existed in our solar system, but we had no way to detect planets around other stars. That changed in the 1990s. In 1995, astronomers detected the first exoplanet orbiting a sun-like star. The planet was huge, about half Jupiter's mass, orbiting incredibly close to its star. This was nothing like our solar system. It was a hot Jupiter, a gas giant in a tight orbit, completing one revolution in just a few days. The discovery was revolutionary. It proved planets exist around other stars. Since then, we've discovered thousands of exoplanets. As of now, over 5,000 confirmed exoplanets exist in our catalogue, with thousands more candidates awaiting confirmation. We've found planets of every imaginable type. Super-Earths, planets larger than Earth but smaller than Neptune. Mini-Neptunes, ice giants smaller than our Neptune but larger than Earth. Hot Jupiters, like that first discovery. Planets orbiting binary star systems. Planets orbiting pulsars. Rogue planets drifting through space without a star. The diversity is staggering. And we've barely scratched the surface. Our detection methods are biased toward finding large planets close to their stars, because those are easiest to detect. Earth-like planets in Earth-like orbits are much harder to find. But we're getting better at it. Several methods exist for detecting exoplanets. The transit method watches for a star's brightness to dim slightly when a planet passes in front of it from our perspective. The amount of dimming tells us the planet's size. The timing between transits tells us its orbital period. The radial velocity method watches for a star to wobble due to a planet's gravitational pull. As the planet orbits, it tugs on the star, causing the star to move in a small circle or ellipse. This motion causes the star's light to shift toward red and blue wavelengths rhythmically. By measuring these shifts, we can detect the planet and estimate its mass. Direct imaging involves actually photographing a planet. This is incredibly difficult because planets are much dimmer than their stars and very close to them in the sky. It requires special telescopes with coronagraphs to block the star's light, revealing nearby planets. And gravitational microlensing occurs when a star with a planet passes in front of a more distant star from our perspective. The planet's gravity acts as a lens, briefly magnifying the background star's light in a characteristic way. Each method has strengths and weaknesses. Transit detections tell us the planet's size, but require the orbit to be aligned just right. Radial velocity gives us mass, but not size. Direct imaging works best for large planets in wide orbits around nearby stars. Microlensing can detect planets at great distances, but only works once. You can't repeat the observation. By combining methods, we can learn a lot about individual planets. Some planets have been studied in enough detail that we know their size, mass, orbital period, orbital shape, and even atmospheric composition. For a handful of planets, we've detected molecules in their atmospheres: water vapor, carbon dioxide, methane, sodium. These detections are done by analyzing starlight passing through the planet's atmosphere during a transit. Different molecules absorb light at different wavelengths. By looking at which wavelengths are absorbed, we can determine what's in the atmosphere. This leads to the possibility of detecting biosignatures, signs of life. On Earth, oxygen is produced by photosynthetic organisms. Without life, Earth's atmosphere would have very little free oxygen. It would react with surface rocks and disappear. The presence of significant oxygen, combined with methane in an atmosphere, could indicate life because these gases are chemically incompatible. Without constant replenishment, they'd react and vanish. On Earth, life produces both. Plants produce oxygen. Microbes and cows produce methane. The simultaneous presence of both is a potential biosignature. Future telescopes might be able to detect these gas combinations in exoplanet atmospheres. If we find oxygen and methane together on a planet in its star's habitable zone, it would be strong evidence for life. But we have to be careful. There are non-biological ways to produce these gases. Oxygen can come from water vapor being split by ultraviolet light. Methane can come from volcanic activity. We need to rule out non-biological explanations before claiming we've found life. This requires detailed atmospheric analysis and understanding of the planet's geology and chemistry. It's not simple, but it's possible. Within the next few decades, we might discover life on another world. Not intelligent life, necessarily. Probably just microbial life, but even that would be profound. It would prove life is not unique to Earth. It would suggest life is common in the universe. And if microbial life is common, maybe complex life is too. Maybe intelligence is too. The implications would be staggering, or we might find nothing. We might search hundreds of potentially habitable planets and find no signs of life. That would be profound too. It would suggest life is rare, maybe extraordinarily rare. Maybe Earth is special. Maybe we're alone, or nearly alone, in the universe. Either discovery, life elsewhere, or no life elsewhere, would fundamentally change how we see ourselves. For now, we don't know. We're searching. The search is one of the most important scientific endeavors in human history. Because the question, are we alone, is one of the deepest and most ancient questions we can ask. For thousands of years, it was purely philosophical. Now, it's becoming scientific. We have tools to actually find out. That's remarkable progress. Let's return to thinking about cosmic scale from a different angle. We've talked about spatial scale and temporal scale. But there's another aspect worth considering: information scale, the amount of information in the universe. Information in the physics sense means the number of bits required to describe a system's state. A single atom can be in different quantum states. To fully describe which state it's in requires information. The more complex the system, the more information needed to describe it. A human brain contains about 86 billion neurons, each connected to thousands of others. The total number of connections is about 100 trillion. The state of all these connections represents an enormous amount of information. Estimates vary, but the human brain might store somewhere between 1 and 100 petabytes of information. That's 1 to 100,000 terabytes. Now, scale that up. There are about 8 billion humans on Earth. If each brain stores 100 petabytes, that's 800 billion petabytes of information just in human brains. About 800 exabytes. That's just human brains on one planet. Now consider all the information in Earth's biosphere. Every organism's DNA. Every neural connection in every brain of every animal. Every structural detail of every cell in every living thing. The total information content is mind-boggling. And Earth is one planet among hundreds of sextillions. If even a tiny fraction of those planets have biospheres, the total information in living systems alone is incomprehensibly vast. And that's not counting non-biological information. The position and velocity of every atom, the quantum state of every particle, the spin of every electron, the polarization of every photon, the curvature of spacetime at every point. To fully describe the universe's state would require more information than we can imagine. Some physicists think the universe's total information content might be finite. The holographic principle suggests that the information in a region of space is proportional to the surface area of that region, not its volume. This is counterintuitive. You'd expect information to scale with volume. But quantum gravity hints that information scales with area instead. If this is true, the observable universe's total information content is finite. Very large, but finite. About 10 to the 123rd power bits. That's a 1, followed by 123 zeros. An incomprehensibly large number, but not infinite. This has deep implications for physics and for the nature of reality itself. It suggests the universe might be fundamentally digital at the smallest scales. That space-time and matter and energy are all emergent from underlying information. That reality is, in some sense, a computation. This is speculative. We don't fully understand quantum gravity or the holographic principle. But it's an active area of research, and it connects to our theme of scale. Because information, like space and time and energy, exists at vastly different scales. A single bit is the smallest unit. A human thought might involve millions or billions of bits. A brain contains hundreds of petabytes. The entire human civilization's knowledge, everything ever written, photographed, or recorded, might total a few hundred exabytes. The total information in Earth's biosphere is vastly more. And the information in the entire observable universe is more still. At every level, the scale increases dramatically. Now, let's consider one more speculative topic: the multiverse. The idea that our universe might be one among many. This is controversial. Many physicists think it's untestable and therefore not science. Others think it's a natural consequence of certain theories. There are different multiverse concepts. The level 1 multiverse is the simplest. If space is infinite, which it might be, then everything that can happen does happen somewhere. There are infinitely many regions of space like ours. In fact, there are infinitely many regions identical to ours. Infinitely many Earths with infinitely many copies of you. This sounds absurd, but it's a mathematical consequence of infinity. If space is infinite and matter is distributed roughly uniformly, then any finite configuration must repeat infinitely many times. This doesn't require new physics, just infinite space. The level 2 multiverse comes from eternal inflation. Inflation, which we discussed earlier, might not stop everywhere at once. It might stop in some regions while continuing in others. Each region that stops inflating becomes a universe, a bubble in an eternally inflating background. These bubble universes could have different physical properties, different constants of nature, different numbers of dimensions, different particles and forces. We live in one bubble. Other bubbles exist, but we can't interact with them. They're beyond our cosmic horizon, forever out of reach. The level 3 multiverse comes from quantum mechanics. In the many worlds interpretation, every quantum measurement causes the universe to branch. Both outcomes occur, but in separate branches. Over time, the number of branches becomes astronomical. Every possible history actually happens in some branch. This interpretation is mathematically consistent but deeply weird. It says there are countless versions of you, experiencing every possible outcome of every decision you've ever made. The level 4 multiverse is the most speculative. It says every mathematically consistent universe exists. Not just universes with different constants or properties, but universes with completely different mathematical structures, different laws of physics entirely. This is Max Tegmark's mathematical universe hypothesis. It's highly controversial and might be unfalsifiable, but it's an interesting idea. If any version of the multiverse is real, our universe's apparent fine-tuning makes more sense. We observe a universe with properties suitable for life because we couldn't exist in a universe without those properties. It's a selection effect. If there are countless universes with different properties, we necessarily find ourselves in one of the rare ones suitable for observers. This is the anthropic principle applied to the multiverse. But we have no direct evidence for a multiverse. It's a hypothesis motivated by theory, not observation. Maybe future physics will provide evidence. Maybe not. For now, it remains speculative. But it's worth thinking about because it relates to scale. If a multiverse exists, our universe, as vast as it is just one tiny piece of something far larger. The observable universe, 93 billion light-years across, containing 2 trillion galaxies, would be just one bubble in an infinite foam. The scale would be even more extreme than we've discussed. Let's bring this back to human experience. We've covered enormous scales, observable universe, multiverse possibilities, deep time, heat, death. These concepts can feel overwhelming. They can make human concerns seem trivial, but there's another way to look at it. We exist at a unique position in the hierarchy of scales. We're roughly in the middle. The observable universe is about 10 to the 27th meters across. A human is about 1 meter. The Planck length, the smallest meaningful length in physics, is about 10 to the minus 35 meters. We're closer to the geometric mean between the smallest and largest scales than we are to either extreme. This isn't cosmically significant. It's just a coincidence of how we measure things. But it means we're well positioned to understand both very large and very small scales. We can study atoms, and we can study galaxies. We can probe quantum mechanics, and we can probe cosmology. We're in the middle, able to look both up and down the scale hierarchy. And we exist at a unique time. The stelliferous era, when stars shine. Before this era, the universe was too young for complex structure. After this era, it will be too old. Stars will have burned out. We exist during the brief window when the universe is interesting, when stars light up galaxies, when planets orbit in habitable zones, when chemistry can become biology and biology can become intelligence. This window will last trillions of years. But compared to the universe's ultimate lifespan, measured in googles of years, trillions is brief. We're living during the universe's youth, its most vibrant period. That's fortunate. We get to see the cosmos at its best, and we're capable of understanding it. That's perhaps the most remarkable thing. The universe has existed for 13.77 billion years. For almost all that time, it was unconscious. Just atoms and radiation following physical laws. But about 4 billion years ago on Earth, chemistry became biology. About 500 million years ago, nervous systems evolved. About a few 100,000 years ago, consciousness emerged that could ask questions about existence. And in the last few thousand years, we developed science, the systematic method for understanding reality. This process happened on one small planet, orbiting one ordinary star in one galaxy among 2 trillion. As far as we know, it's happened only once. We might discover it's happened elsewhere too. But for now, we're the only example we have of the universe becoming aware of itself. That's special, not in a cosmic sense. The universe doesn't care, but in a real, meaningful sense. We're matter organized in a way that allows it to contemplate its own existence. That's rare, maybe extraordinarily rare. And it's valuable, because without consciousness, without observers, the universe would be meaningless. Not in the sense that it wouldn't exist. It would exist. Stars would burn, galaxies would rotate. But there would be no one to know about it. No one to understand it. No one to appreciate it. Consciousness creates meaning by its very existence. When you look at a sunset and find it beautiful, you're creating meaning. The sunset would happen whether you saw it or not. But the beauty exists only because you're there to experience it. Beauty isn't a property of the sunset. It's a property of your response to the sunset. The same is true for all meaning and value. They're not inherent in the universe. They're created by conscious observers. The universe is vast and ancient and mostly empty. But the parts that matter, that have meaning, are the parts where consciousness exists. And that might be a very small fraction of the total. Perhaps an infinitesimally small fraction. But it's the fraction that matters. Without it, the rest is just stuff following equations. With it, the universe becomes knowable, experienceable, meaningful. So, yes, we're tiny. Yes, we're brief. Yes, the universe is indifferent to our existence, but we're not indifferent. We care, we experience, we understand. And that transforms tiny and brief into something profound. Because in the entire observable universe, spanning 93 billion light-years and containing 2 trillion galaxies, we might be among the very few, possibly the only, beings capable of understanding the true scale of existence. That's not nothing. That's everything. When you think about it this way, the scale of the universe doesn't diminish us. It contextualizes us. It shows us where we fit in the grand scheme. It reveals how unlikely and precious consciousness is. It demonstrates the power of intelligence and curiosity to comprehend reality. We're products of the universe, made from its atoms, following its laws, embedded in its structure, but we're also separate in a sense. We can step back and observe. We can measure and calculate and understand. We can appreciate beauty and create meaning. The universe is unconscious, matter and energy. We are conscious, matter and energy. That difference is everything. So when you look up tonight, remember, you're not just seeing distant lights. You're seeing into the past. You're seeing atoms forged in ancient stars. You're seeing the same physical laws operating across unimaginable distances. You're seeing the cosmic web that emerged from tiny quantum fluctuations in the first moments after creation. You're seeing everything that is, and was, and will be, stretched across space and time in a grand tapestry of existence. And you're part of that tapestry. Every atom in your body has a history stretching back 13.77 billion years. The calcium in your bones was created in a supernova. The iron in your blood was forged in a dying star's core. The water you drink cycled through Earth's hydrosphere for billions of years. You're not separate from the universe. You're continuous with it, an expression of it, a way it experiences itself. That perspective can be liberating. Your problems, while real and important to you, exist in a context so vast that they're almost vanishingly small. But your experiences, your consciousness, your ability to feel and think and wonder, those are precious beyond measure. Because, as far as we know, consciousness is rare. Maybe the rarest thing in the universe. The universe is made mostly of dark matter and dark energy, things we can't see or touch or directly interact with. Ordinary matter, the stuff we're made of, is only 5%, and of that 5%, most is locked in stars or dispersed as gas. A tiny fraction forms planets. An even tinier fraction forms living worlds, and on those worlds, consciousness is a recent development, a fragile, temporary phenomenon. Yet here you are, conscious, aware, capable of understanding that you're one arrangement of atoms among countless others, capable of grasping the scale of the universe even though you're infinitesimally small within it, capable of appreciating beauty even though the universe contains no inherent beauty, capable of creating meaning even though the universe follows meaningless mathematical laws. You're a statistical impossibility that somehow exists anyway. The product of 13.77 billion years of cosmic evolution. The descendant of the first replicating molecules that appeared in Earth's oceans billions of years ago. The inheritor of knowledge accumulated over thousands of years of human civilization. And an active participant in the ongoing project of understanding reality. Everything we know about the universe came from curious humans, asking questions and following evidence. Every measurement, every theory, every discovery. All of it was done by people not fundamentally different from you. They weren't gods or superhumans. They were curious individuals who dedicated their lives to understanding, and their work built on the work of those who came before. Newton famously said, if he saw farther, it was by standing on the shoulders of giants. He meant he built on previous discoveries. But the metaphor extends. All of science is cumulative. Each generation builds on the last. Knowledge grows, understanding deepens, and you're part of that process. Even if you're not a scientist, even if you never make a discovery, you're part of the civilization that does. Your taxes might fund telescopes. Your curiosity might inspire future scientists. Your existence contributes to the collective human project of making sense of the cosmos. Let's think more concretely about what some of these cosmic structures would actually look like if we could see them properly. We've discussed galaxy clusters. The Coma cluster contains over 1,000 galaxies, packed into a region about 20 million light-years across. If you could somehow hover in the middle of this cluster, what would you see? The night sky would be absolutely spectacular. Instead of seeing a few thousand stars like we see from Earth, you'd see hundreds of galaxies scattered across the sky. Many would be visible to the naked eye. Some would be large and bright enough to show their spiral structure without a telescope. The sky would never be truly dark. The combined light from hundreds of galaxies would create a permanent glow, and the galaxies would be noticeably moving over thousands of years. You could watch them orbit the cluster's center, occasionally colliding and merging. Now imagine being in a void, one of those enormous empty bubbles in the cosmic web. The nearest galaxy might be hundreds of millions of light years away. The night sky would be almost completely black. No Milky Way band, because you're not in a galaxy. No nearby galaxies visible to the naked eye. Just profound darkness. Maybe a few extremely faint smudges if you had exceptional vision and knew exactly where to look. The cosmic microwave background radiation would still be there, of course. But it's microwave radiation, not visible light. You can't see it. Without specialized instruments, you'd see almost nothing. Just blackness, and maybe a few of the brightest quasars in the entire universe. It would be lonely, isolating, a reminder of how empty most of the universe really is. Or imagine being near a black hole, not close enough to be in danger, but close enough to see its effects. The black hole itself would be invisible. It emits no light, but if it's feeding, consuming matter from a nearby star or gas cloud, there would be an accretion disk around it. Matter spiraling inward, heating up to millions of degrees, emitting X-rays and visible light. The disk would be incredibly bright, brighter than any star, and it would be moving. You could watch material spiral inward toward the event horizon. As matter approaches the event horizon, several strange effects would become visible. Time dilation would cause material near the event horizon to appear to slow down. Light from that material would be redshifted, shifted toward longer, redder wavelengths, and gravitational lensing would distort the view. Light from stars behind the black hole would be bent around it, creating a bright ring. You'd see stars that are actually behind the black hole appearing to hover around its edge. This is the black hole's shadow, the dark region where no light can escape, surrounded by a bright ring of lensed light. The Event Horizon Telescope actually captured an image of this for the black hole in M87. The image shows exactly what theory predicted: a dark center surrounded by a bright ring. It's remarkable that we can predict what something looks like based on mathematical equations and then actually see it matches. That's the power of physics. It tells us what to expect, even in the most extreme environments. Environments we'll never visit physically, but can explore mathematically. Let's consider another thought experiment. What if you could travel backward through cosmic time? Start in the present and move backward. First, you'd see human history unfolding in reverse. Cities shrinking, technology vanishing, civilizations rising and falling. Back through the Middle Ages, ancient Rome, ancient Egypt, the first human settlements. Back through the Ice Ages, as glaciers advance and retreat. Back through hundreds of thousands of years of human evolution. Then you'd see other species. Homo erectus, Australopithecus. Back through millions of years of primate evolution. Then, mammals diversifying after the dinosaurs die. Wait, in reverse, that would be dinosaurs appearing, rising from extinction, roaming the Earth for over 160 million years, then vanishing as you go back further, reptiles becoming less diverse, amphibians appearing, fish diversifying in the oceans, then simpler and simpler life forms. The Cambrian explosion in reverse, as complex animals become simple ones, back through billions of years of mostly microbial life, single cells growing simpler, until finally life disappears. Earth becomes a sterile, hot, volcanic world. Still going back, you'd see the solar system forming, planets coalescing from dust and gas. The sun igniting as hydrogen fusion begins, the solar nebula before that. A cloud of gas and dust, rotating and collapsing under its own gravity, then going back further into the galaxy. You'd see the sun's birth cloud dissipating, other stars forming and dying around you. The Milky Way gradually becoming younger, smaller, less organized. Stars becoming more metal-poor, containing fewer heavy elements because fewer supernovae have occurred yet. The Milky Way merging with other smaller galaxies, but in reverse, so it's splitting apart, ejecting matter. Going back further, galaxies throughout the universe become smaller and less structured. The cosmic web becoming less defined, voids shrinking, filaments dissolving, galaxies turning into clumps of proto-galactic material. Then just diffuse clouds of gas, mostly hydrogen and helium with traces of lithium. The first, stars unforming, their fusion processes running backward, heavy elements splitting into hydrogen. Then the cosmic dark ages. No stars. Just cooling hydrogen and helium gas, slowly becoming more uniform. The cosmic microwave background becoming visible light, then ultraviolet, as you go back toward the moment of recombination. Then the universe becoming opaque. A plasma of nuclei and free electrons scattering photons constantly, going back through the first few minutes, complex nuclei splitting apart, protons and neutrons unforming into quarks. Then, earlier still, all matter and energy compressed into an impossibly hot, dense state. The first fraction of a second when inflation occurred. And before that, we don't know. The physics breaks down. Our theories stop working. There might have been a true beginning, a moment when time itself started. Or there might have been something before, another universe, a cycle, a multiverse spawning ground. We don't know. This thought experiment reveals something important. The universe has a history, a narrative arc from simple to complex, from uniform to structured, from unconscious to conscious, at least in some places. The arrow of time points in a definite direction, toward increasing entropy overall, but toward increasing complexity in local pockets like planets. Understanding this history helps us understand our place. We're not eternal beings in an eternal universe. We're temporary patterns in an evolving cosmos. products of a specific era, the stelliferous era, the age of stars and galaxies and potentially life. This era will end eventually, but for now, it's ongoing, and we're experiencing it. Let's think about one more scale question. How much of the universe can we actually affect? Our sphere of influence. Right now, our influence extends only to Earth and its immediate vicinity. We've sent probes to the edge of the solar system. Voyager 1 is about 14 billion miles from Earth. Still in the solar system, technically, but very far. That's the farthest reach of human-made objects, about 0.002 light-years. Compared to the observable universe's 93 billion light-year diameter, that's nothing. Our sphere of influence is absurdly tiny, but it's growing. Slowly, very slowly, light from Earth, radio signals, television broadcasts, all propagate outward at light speed. The first radio broadcasts were in the early 20th century, about 100 years ago. Those signals are now about 100 light-years away, forming an expanding sphere. Any civilization within that sphere could potentially detect our signals. Though they'd be very weak by the time they got that far, probably indistinguishable from noise. Still, in principle, we're detectable out to about 100 light-years. That's our information sphere. The region where anyone could know we exist based on our electromagnetic emissions. It's growing at the speed of light. In 1,000 years, it'll be 1,000 light-years in radius. In 1,000,000 years, 1,000,000 light-years. Assuming we keep broadcasting, which we might not. We might switch to more efficient directed communications that don't leak into space. But for now, we're announcing our presence to a growing sphere of the galaxy. In the far future, if humanity survives and spreads, our sphere of influence could grow much larger. If we colonize other star systems, we directly control multiple stars. If we spread throughout the galaxy, we could affect billions of stars. But there are limits. The observable universe is 93 billion light-years across. Even if we could travel at light speed, which we can't, and we started spreading today, we could only ever colonize a sphere that expands at light speed. After 1,000,000 years, we'd control 1,000,000 light-year sphere. After 1 billion years, 1 billion light-year sphere. But the universe is expanding, and the expansion is accelerating. Regions beyond a certain distance are receding faster than light can reach them. We can never affect those regions, no matter what we do. The cosmic event horizon limits how far we can ever influence. Calculations suggest that's about 16 billion light-years away currently. Everything within that distance could potentially be reached, eventually. Everything beyond cannot. We're limited not just by technology, but by the fundamental structure of space-time. This has profound implications. If we spread as fast as physically possible, the most space we could ever affect is a sphere about 32 billion light-years in diameter, less than a third of the observable universe's current diameter. And most of that sphere would be empty void anyway. The actual number of galaxies we could reach is limited, maybe a few 100 billion at most, out of 2 trillion total. So even in the most optimistic scenario, we could never reach most of the observable universe. Most galaxies will forever remain beyond our grasp. They're receding too fast. By the time our influence could reach them, they've accelerated beyond the horizon. This is true for any civilization, anywhere in the universe. Each one has a finite sphere of potential influence. They can spread only so far before expansion carries distant regions beyond reach. If intelligent civilizations are common, the universe might be full of them, each confined to its own expanding bubble, forever unable to meet or communicate because space expands too fast. This is a sobering thought. We might be truly alone, not because intelligent life is rare, but because the universe is too large and expanding too fast for civilizations to ever find each other. Even if 1,000,000 civilizations exist in the observable universe, if they're randomly distributed, the average distance between them would be enormous. Millions of light years. By the time signals traveled that far, both civilizations might be extinct. The timescales involved are just too long. Even at light speed, communication would take millions of years. Trying to have a conversation would take millions of years per exchange. Civilizations rise and fall on shorter timescales than that. It's a lonely universe. But maybe that's okay. Maybe it means each civilization has room to develop without interference, without competition or conflict with others. Each can explore their local region of space, develop their own culture and technology, and make their own choices about their future without cosmic neighbors watching or judging. There's a freedom in isolation, a chance to be ourselves without external pressure. So, when you feel small, when the scale of the universe overwhelms you, remember this. You're small, yes, but you're conscious. You're capable of wonder. You're able to comprehend the vastness even while being tiny within it. That's remarkable. That's valuable. That's meaningful in the deepest sense. The universe is big. You're not, but you're aware of that difference. You can think about it. You can marvel at it. And that makes you, in your own way, as significant as anything that exists. Because significance isn't about size. It's about meaning. And meaning comes from consciousness, from experience, from the ability to understand and appreciate. You have that ability. Use it. Look up at the stars. Ask questions. Seek answers. Wonder about existence. You're participating in one of the most profound processes in the universe. The universe experiencing itself, trying to understand itself, marveling at itself. That's what consciousness does. And you're part of it. For a brief flash, you get to be aware, to think, to feel, to understand. Don't waste it worrying about cosmic insignificance. Embrace cosmic connection. You're made of stars. You're part of the universe. You're how it knows itself. And that's extraordinary. Thank you for journeying with me across these scales, from where you sit to the edge of everything. The universe is larger than we can truly comprehend, older than we can fully imagine, more complex than we can completely understand. But we can grasp pieces of it. We can measure it. We can explore it. We can marvel at it. If this exploration moved you, please like this video and subscribe to the channel. It helps others discover this sense of wonder. And remember, you're small, yes. Impossibly, incomprehensibly small. But you're part of something infinite. And that makes you, in your own way, infinite too. Good night, and keep looking up at the stars.